the real world. Right, it doesn't, it just fits math. All right, we're gonna look a little further. I don't want to leave substitution quite yet. It's an important subject, and I want to go over a few problems just so you have a little variety. And substitution. So, start to look at this problem. Of course, this function doesn't look like anything we know the antiderivative of. But we just get an intuition how can we make this simpler? I mean, obviously, square root's going to stand down. So how might we eliminate that? We could take a u that will make the square root disappear. So we're going to be able to substitute that in. But what are we going to do about dx? Well, you can find the derivative on both sides here. This would be 2u du equals 1 dx. Again, we're using these, they're called differentials, as notationally to help us move along. They're not real quantities. So substituting in, we get 1 over plus u, and then our dx is 2u. Well, we've eliminated the square root, but we still have this function 2u, 1 plus u. And we don't, we saw how to deal with this yesterday. We take this rational expression and we divide out. So dividing 2u by u plus 1. Okay, that's 2. 2u plus 2 minus 2, so it's remainder minus 2. So this becomes the integral of 2 over 1 plus u plus minus 2 right? Just plain 2. All right, now this is pretty straightforward. Antiderivative is going to be 2u plus minus 2 log absolute value of u plus 1 plus c. And at this point, all we have to do to finish up is to substitute back. So we get 2 square root of x minus 2 log of square root of x plus 1 plus our constant of integration. Kind of a exercise in finding derivatives. You might want to go ahead and find the derivative of this function and establish for yourself that you end up back here in 1 plus square root of x. A little paperwork to do here for a second. before I go forward, we're gonna go over a few more examples. Anyone have like a homework question or a general question? Okay. All right. Next problem, we're gonna actually attack it in two different ways. Now, I guess I'll just go straight forward and attack this in seems like obvious. We'll try and simplify what's under the square root here. See if we can use that to our advantage. Again, I'm going over stuff I've already worked out. When you're doing this, frequently you make a substitution and you follow it through. It just doesn't work. It's like you went down a blind alley and you have to kind of backtrack and say, maybe that wasn't the substitution that I needed. But in any event, after a little while doing these, you get a little intuition as to what might work, what might not. So here we're gonna try u equal to 1 minus x squared. And so our du is negative 8x dx. And seeing this x here, this x on top, we start to think, this could work out. All right. So let's write this du over minus 8 is x dx. That'll make the substitution easier. So what does this become here? This becomes, well, x dx becomes du times x 1 over 8, and square root of 1 minus 4x squared becomes 1 over square root of u. And then we look at that and we say, that's an integral I know how to do, because this is just u to the minus 1/2. I can use the reverse power rule. So what's that going to give me? U to the 1/2 over 1/2, which is just 2, plus constant integration. We can simplify here, but so that strategy worked pretty nicely. However, we go back to the original problem here. Look at this and something might catch your eye about it. You think, I remember there's some function 1 minus x squared that you know the antiderivative of that, don't I? Understand it? Close. This is the antiderivative of this would be the inverse sine. The tangent would be 1 plus x squared. A slightly different pattern, but good that you're pattern matching is what you need to do here. So, thinking about that, all right, what can I do? What can I do along the lines of trig functions? Well, 1 minus 2x squared. That should ring a bell, make you think of Pythagorean identity, kind of in reverse. And that suggests, I gotta look at my notes, that suggests something like, let's set x equal to 1/2 sine of u. Well, where did I get that from? Well, x squared is 1/4 sine squared u, and when I plug that in here, I'm going to get 1 minus sine squared u, which will be the cosine squared of u, which conveniently will disappear when I find its square root. All right, that doesn't mean this is going to work. We still have this x dx to worry about, so let's see. Let's see what happens here. So dx is 1/2 cosine of u du. All right. So let's see what happens when we plug this all in. Now I'm wondering, will this work? Kind of like those, sometimes you like to have like an adventure video game. More than one way to beat the cave troll. Sometimes you just want to get around him. Sometimes you want to walk straight through. All right. So on the bottom, plugging this in, again, I have 1 minus sine squared. Square root of 1 minus sine squared is square root of cosine squared is just going to be cosine of u. Well, my dx, I have that. That's going to be 1/2 cosine u du. Oh, isn't that convenient? So all I really have end up is this x, which I'm going to substitute and get 1/2 sine of u. All right, so I'm going to cancel here. End up with 1/4 sine u du. That's something I know how to find the antiderivative of. That's going to be, well, I'm going to get a negative sign, right? It's going to be negative cosine, so negative 1/4 cosine of u plus constant of integration. Now we have a little more of a challenge here. How are we going to get rid of the u? Because this is our substitution. Well, we want this cosine u to look like sine. How do we do that? 1/4 square root of 1 minus sine squared u. That's pretty obvious. Again, I'm just using the Pythagorean identity here. And, get negative 1/4. Running out of word space, but I get negative 1/4 square root of 1 minus, well, it's going to be 1/4. It's going to be 2x squared. I think when you get done with all the constants, I think that's what you're going to get here too. So again, there's more than one path. And you know, your best bet to learn this is try the homework. You know, don't expect these to be real straightforward. You might have to try substitution, get a little intuition as to what might work. All right, I'm going to do one more. Kind of looks a little bit like all these, because I wish I would have put it in, you know, all the work in my notes, because I have I recall this one's particularly thorny. This one comes as a definite interval. You're going to want to actually find a number when we're done. Right. So the obvious substitution here is either going to be, you're either going to put in x plus 4, or maybe, you know, we're either going to have u as x plus 4, or we're going to have u as u squared as x plus 4. I think we're going to go with the former. That makes du equal to dx. That's nice and simple. And let's not pay attention to these right now. This just becomes what? Underneath, we have the square root of u. On top, well, we have to look here. What's x is equal to u minus 4. That's so sloppy. U minus 4. du. Well, maybe I'm wrong. This doesn't look bad at all. Because this, of course, is integral of square root of u minus 4 over square root of u. Both of these should be fairly simple because we write these exponentially. We can, of course, immediately use the reverse power rule. So 3 halves, 2/3, and this one is going to be 4 times 1/2 over 1/2, 8. Now we just need to substitute u back. So start constant integration. Oh, but we want to go a little further. All right, so we could substitute back and get x. But if you recall, that formula says that integral from a to b of f prime of x, prime of x, that becomes what? That becomes the integral where u is g of x. That becomes g of a to g of b, f prime of u, du. So that tells me I can modify these. So how does that work? So these are the x's. So if x is 4, and u is what? 8. And if x is 0, and u is 4. So I can evaluate this between 8 and 4, just the way it is. Any questions about any of these, about substitution in general? You have a homework problem, you're having trouble with doing this? Sure. Sure.
Yeah, I want to know how.
You're trying to hide that from me, huh?
Yeah, so you have u minus 4 over square root of u. How do you simplify that to square root of u minus 4 over square root of u? Second number. Yeah, how do you simplify
From this to this?
Yes.
You gotta watch out, I make mistakes. So I have u minus 4 over square root of u. So that's u over square root of u minus 4 over square root of u.
You multiply by the square root of u. Yeah. Okay, got it.
I mean, this is u to the 1 and this is u to the 1/2. And 1 minus a half is half. Minus 4 times u to negative 1/2. Yes?
I'm a little confused about how you use the u equals d of x, where you don't have to evaluate by the interval that's on there. You have the a to b.
Yeah, A to B.
Yeah. How do you use that to get this interval here, 4 to 8?
There's a 50-50 chance I didn't do it right. Because I never do this. I just like, why would I want to learn that? I just always would go. I'm going to answer your question, by the way. We'll just see. So I would always just say, oh, okay, so here u is x plus 4, right? So I would always just go say x plus 4 to the 3/2 over 3 minus 8 x plus 4, from 0 to 4. Life is short, there's two ways to do something and you like one better, go ahead, do it. You may like this way better. Okay, so how did I get from integral 0, 4, right? Well, when I do the substitution, I can say from g of 0 to g of 4. Well, this is the function. This is the function g here. U is, we just interchange these, unfortunately. So, u of x, is x plus 4. So that maybe would have been nicer, say u here. So what does that become? Well, u of 0, that's 4, and u of 4 is 8. Just a question of, you want to switch back to the x coordinate system from the u coordinates and use our original, or switch the limits. I'm going to go there for just a second. Oversimplify it. Let's say I wanted to do something really It's really simple. I want the integral from 0 to 2 of 4. Say, all right. I want to do a substitution. I need to, but I want to do a substitution. But before I do that, let's just draw a little diagram here. So here's our function 4, f of x, and we're going from 0 to 2. We want this area. So I'm going to make a substitution. So I'm going to say u equals x plus w. All right, so du equals dx. Now I have the integral from 10 to 12. I'm just plugging in my limits here. And I have 4 du. All right, well, what does that look like? Well, function didn't change. All I really did is still 4. Now I'm switched over from 10 to 12. And here it's really obvious that the two areas are going to be the same. Now, I guess what's not so obvious is, you know, what if we don't have a linear substitution here? It's something simple. Well, I think that's about 2 or 3 days in an analysis class to prove that. So we're not going there. But you can take. Don't take my word for it. You can look in the book. But that formula works. That you can translate the limits, or you can convert back to x and use the original limits. And they both.
I just didn't know how you ended up getting 4 and 8, and you changed the coordinates.
Oh, I just used this this transformation here. I mean, here it's more obvious. U is x plus 4. These are the x's. These are the u's. So that's why we just end up adding 4. The translation might be more complicated. If you know u is square root of this, it's a different function, or it could be a trig function. That's your substitution. Right. Someone else's. Okay, is that good? Are we good with substitution for now? Okay. Anybody who's come in late, there will be a video if you want to see the beginning of class. Since I marked you here, I probably won't remember to send you an email, so if you want to get it, you might send me an email and I'll send you a link. All right. So having worked our way through this is, the second half of calculus. We haven't completed all of integrals, but we've learned a bit of mechanics. Having learned how to do this, okay, is that all there is? Just finding the area under a curve? No, there's a little more. We'll try and cover here section 5.6 is area between curves. what do we mean by that? Well, we have some function, as before, f of x. But we have another function, g of x, and between two limits, a and b, we want to find just the area in between them. Okay? Well, if we have this scenario where f of x is always greater than g of x, so should be pretty obvious. The area below f of x is just all this area. And the area below g of x is just this area. So if we want to find the area between f of x and g of x, we ought to just be able to subtract. But of course, we know that we can combine these. This is just, we can just combine it into one integral. And we can get our area. Now, this is simple, but it brings up some questions. What happens if these functions aren't above the line? In other words, there's 0 and f of x is here, and g of x is down here. And we still want this same area. Will this still work? Here's something we certainly could do. We could just take each of these two functions and add some constant, push them up above the axis here. Push this function up, push this function up. And then we'd be back to this scenario here, where we know we would get the area we want. But can we do this? Is that legit? So let's take a look. We have this function a to b f of x plus whatever that constant needs to be, minus the integral a to b of g of x plus c. Well, again, we can expand this a to b f of x dx plus a to b c dx minus a to b g of x dx plus c plus integral a to b c dx. But you ought to be able to see right here that here we're adding some value, and here we're subtracting it. So we can can just cancel these, and we end up back here with the same formula. So we don't have to worry where these are on the axis, on the y-axis. They can be below or above. That doesn't affect the result. So that's one complication you don't have to worry about. Now, here's a complication we do have to worry about. What if our f of x is kind of like this? And our g of x, unfortunately, is kind of like this. And here's our a, here's our b. And what we want is the area between the curves. Well, if we just do a regular integral here, what's going to happen is we're going to get positive area here, negative area here. So we're not going to get what we want. Now, there's two ways to think of it, which both really the same. Just say, all right, just pick up my sleeve, just take the absolute value of f of x minus d of x, and now we just magically converted this. But the problem now comes back to how do we calculate this. To do this, we need to know where these curves intersect. What is that? So let's call this, I call this C1, and I'm going to call this C2 for lack of originality. So to evaluate this, now we want to evaluate A to C1 of, let's just call this, I don't know, d of x. We want to evaluate from A to C1 of d of x plus, well, now we're going to have to reverse the sign, minus of C1 to C2 d of x, and then just add from C2 to b of d of x. So in other words, we add up this value, we get a negative for this area, but we reverse the sign and the x. So that gives us a way to deal with the possibility that these might intersect. All right, well, I guess we should try a problem like this. Just see how it looks. So here's a typical problem. Find the area enclosed by y equals x squared, y equals 2x minus x. Well, first thing, will help is if we have some idea what this is going to look like. So let's try and graph this. Y equals x squared is pretty straight. parabola. Just going to go through 0, 0. Plot 1. We're just trying to get an idea here. So if I plot 1, I get 1. And then what's going to happen next? It's going to be upside down, so it's going to be like this. Okay. So I want to find this kind of peculiar area here. And I know I can just see that 0, 0 is one place that these intersect, but I want to find this point, right? This is going to be my A, this is going to be my B. So I'll set these equal. And I'll get x squared equals 2x, x squared equals x, or x squared minus x equals 0. And by factoring, I can see immediately that the 2 points where they're going to meet are 0 and 1. I guess that wasn't 1 over there. I guess it was over here. So here's my integral from 0 to 1. This isn't like my previous example, like a sine wave where there are going to be multiple areas. It's just one area. It looks like this is the f of x. This is the one on top. So 2x minus x squared. That's f of x. This is my g of x minus x squared dx. And now I have a pretty simple integral to solve here. Just need to use the power rule. So simple, let's give it a shot. 2x minus 2x squared dx becomes x squared minus 2/3 x cubed from 0 to 1. So it just becomes 1 minus 2/3. It's 1/3. It's too easy to skip. All right. All right, we're gonna break now for a few minutes. All right, before I go, any questions? Okay, so we're gonna look at a same kind of problem, but with a different challenge. Want to find the area between these two curves. We'll take a look at it, but I guess if you note right away, one of the points of intersection is going to be 0, right? Plug in 0, you get 0. You plug in 0, you get 0. Now let's take a look at this a little brighter. Take a look at what this actually looks like. Any of you CS majors out there want to see an example of really nice user interface? I just type what I think I want to type here, and Desmos seems to figure it out. It's just really well done user interface. Okay, so that's one of my functions, and let's do the fourth. That's X. Okay. Now, we could set these equal, couldn't we? Okay, x over x squared plus 1 equals x to the 4th times x. And we could try and solve for x here. We could try and solve for x here. I guess we might as well. X equals square root plus 1. What would we do now? We got to square both sides, right? To get rid of that square root. I'm so sloppy, Mr. Schoenbrun. 4th times x squared equals squared plus 1. Squared equals x squared plus 1. Oh my goodness. X to the 4th minus x squared. I've got 8th degree polynomial here. No, it's not 8th. It's 10th degree polynomial. As my grandmother would say. Oy vey. Well, as long as I didn't need a exact, and when I say exact, I mean, to infinite place, I can use some technology here. I'm sure there are a number of options. One option is just your simple TI calculator. Put both these functions in, and there's a calc function. Calc 5, intersect. Now, for some odd reason, I never can get calc 5 intersect to work. You guys are smarter than me. But I can always just find the difference between these two. I could always put in the equation x squared plus 1 minus x to the 4th minus x, and ask for the root, ask for where it's equal to 0. That I can figure that out. But since we have Desmos up here, and again, Desmos has this wonderful user interface, I'm just going to poke here, and what does it tell me? It says 1.181. So 0 to 1.181. Well, we could do both of these. Could do, this is f of x, this is g of x. We certainly could do from 0 to 1.181 f of x minus g of x. We could do that analytically, but why? We're not going to get an exact number anyway. You can just plug this into your TI to the integral function, and you'll get this area. So again, I just want to point out that sometimes you just let technology handle the ugly parts of this. There might be a homework problem like this. I'm not sure. Okay. I think that's all I have for today. Again, on Tuesday, we're gonna look at some other applications of using integrals, and then on Thursday we'll have a review. And please take a look online. I put a review sheet, but don't just look at the final review sheet. References the other two. Look at everything, anything you have questions on for the whole year, for the whole semester, bring them. We'll go right back to the beginning, start at limits and move through, answer questions, review, refresh your memory. And that's kind of it that'll be it for the semester. All right, I'll be here for a few more minutes and I'll be down in my office.